Alright, in the next section we will be looking at how to actually calculate equilibrium constants. So far we've sort of been given equilibrium constants, or we have had equilibrium concentrations and we can write an equilibrium expression to find that. Well, we're going to do a similar thing, but what if we don't know our equilibrium concentration? So then how can we find it? So we have a question. So it says you have a closed system that contains 1 times 10 to the minus 3 molar H2 and 2 times 10 to the minus 3 molar I2 at 448 degrees C. So the system is allowed to achieve equilibrium, and it says analysis of the equilibrium mixture shows that the concentration of HI is 1.8 times 10 to the minus 3 molar. It wants to know what is the Kc value for this reaction at 448 degrees C. And they give us a reaction equation. So we see I2 or H2 plus I2 gives us 2HI. And they have given us some concentration values. So the first one, they gave us the concentration of H2. Okay, but this is the concentration of H2 at the beginning of the reaction. So remember, we're trying to look for the reaction at equilibrium, so not the initial concentration. They also give us the concentration of I2, but again, this is at the initial concentration. So we know that the reaction has occurred, and that at some point we've reached equilibrium. And lastly, they give us an equilibrium concentration for HI. So we can write a Kc expression, the products over our reactants. So concentration of HI squared over hydrogen times iodide will give us the Kc value. The issue is these refer to equilibrium concentration. They don't refer to just regular instantaneous concentration or initial concentration. Okay, so we need to know actually at equilibrium what are these concentrations. So how can we figure that out? Well, we do that through an ICE table. So we're going to set up a table something like this for a lot of these problems. So the first thing, just set up some boxes, write out your equation, set up some boxes. And so generally speaking, you'll have a line just for the words ICE, which are initial, change, and then equilibrium. Okay, then you'll write your reaction, and each of the species in the reaction should line up with a column. Okay, then your plus and your arrows will line up with just the lines. Okay, so what goes in these boxes are pretty much exactly what you expect. So initial means the initial concentration. Okay, so this is exactly what we started from. So they told us this initial concentration, and they told us this initial concentration. But what about HI? How much HI did we start from? Well, we started, of course, with no HI, because before we've actually mixed the reactants, then we have no product. So at the moment they're mixed, there's no product yet. Okay, so our initial concentration of HI, or of our product, would be 0. But what they do tell us is this value. So the equilibrium concentration of HI. So now what we have to do is we have to fill in the rest of the table. So we're looking for this value and this value in order to determine Kc. So how can we do that? Well, first, we need to fill in the change line. Okay, and based on our reaction equation, we know that H2 and I2, so we know these are decreasing, okay, since they're going away and forming product. We know our product is increasing. So we'll represent H2 and I2 as just minus X. Why minus X? Because we know that they're going down by some quantity, and we're going to represent that as X. Minus X because it's going down, and minus 1x because each one of them has a 1 as a coefficient. Okay, and then HI will represent as plus 2x. Plus 2x because we know it's going up by the same quantity, but 2 times that quantity. Okay, so you'll base those just basically on their coefficients. And so what we end up with in our equilibrium line, well, we'll get there. So we can actually solve for those concentrations. But for now, let's solve for x. So if we know 0 plus 2x is equal to 1.87 times 10 to the minus 3, okay, represented here, then we can solve for x based on this equation. Okay, so x will be equal to 1.87 times 10 to the minus 3 divided by 2. So just dividing by 2 here and dividing by 2 here. Okay, which gives us 9.35 times 10 to the minus 4. Now bear in mind, that's not the equilibrium concentration. This is our X value. Okay, so if now we know X is 9.35 times 10 to the minus 4, what can we do with that? Well, we know that this equilibrium line is this concentration minus X will give us this. Same thing here. So this concentration minus X gives us this. Okay, so we just set up those values, or set up those equations. Okay, so our X value now we know is not just X, but it's minus 9.35 times 10 to the minus 4. Or 9.35 times 10 to the 4, not the minus. The minus comes from the fact that it's minus X. Okay, so just subtract that from our initial concentration, and that gives us everything we need to know about our equilibrium concentration. Now suppose we want to calculate Kc. So remember our Kc expression? So just the same way we've been setting them up, we can set up a Kc expression this way. And now we can plug in our numbers. So just literally taking from our initial line, okay? So remember it's products over reactants. So our only product is HI, so that will come here. And then our two reactants will go on the bottom. So these two come down here. Okay, so I'll get rid of some of my scribbling to make it a little more clear. Okay, so all we've done is we've taken our equilibrium line and put that into our Kc expression. And we can do that math, and we can calculate this to get a Kc value of 50.3. Again, right now I'm not so concerned with what that value is, although we've come up with it. Okay. So that's how we go about finding the Kc value given that information. So we'll use the ICE table and then just fill in each of the boxes and then plug the equilibrium concentrations into our Kc expression. Okay, so here's one for you to try. So it says an aqueous solution of ethanol and acetic acid, each with a concentration of 0.810 molarity, is heated to 100 degrees C. And it says at equilibrium, the acetic acid concentration is 0.748. It wants us to calculate KEQ at 100 degrees C for the reaction. And it gives us the reaction equation. So here we see ethanol and acetic acid combining, okay, to give us our products. Okay, so see if you can set up an ICE table for this, fill it in, and then calculate your Kc value. Or here they're saying KEQ, but remember, that's the same thing as saying Kc. Okay, so pause the video, give this one a try, see how far you get. If you get stuck, that's okay. Just start the video again and we'll go over it together. Okay, so the first thing we want to do is to set up our ICE table. And I've gone ahead and set one up just based on our equation. Okay, so let's take the information they gave us and see if we can figure out where to put it. So one thing I can go ahead and tell you is that for the liquid, remember that in our equilibrium expression, pure liquids and solids do not appear in our equilibrium expression. So the very first thing we can do here, and I'm going to grab a different color just so it will stand out a little bit better when I write on top of here. Let's see, what can we choose? Let's use red. No, red might be a bad color. Let's do let's do blue, bright blue. Okay, so we can go ahead and just X out this column because we know that it is not a part of our equilibrium expression, so there's no need to even think about it. Okay, the next thing we can do is that we know initially we start out with none of our product. And now we can fill in what we do know. So it also tells us that we start out with 0.810 and 0.810, and those are in molarity. I'm going to leave off the units just to save some space, but those are both in molarity. And what we do know is that the acetic acid concentration at equilibrium is 0.748. Okay, so a little bit different here. So before we knew this concentration, but this time it's told us the acetic acid concentration. Okay, so what can I do here? Well, instead I'll put it here. So 0.748. And again, that's a molarity. So it doesn't matter what information they give us about the equilibrium, we can still fill in this table. Okay, so what do I know now about the change line? So I know this is changing by minus x. I know this is changing by minus x. One more thing I know is that my product is going up by just plus x, because I only have a 1 as a coefficient in each of these. Put my toolbar away. I'm sure that's driving some people crazy. Okay, so what can I do now? I need to solve for x, basically. Okay, so those are the 3 pieces of information they gave us. So now all I have to do is set up this equation. So I can say 0.810 minus x is equal to 0.748. Okay, so now if I just So let's do this. Let's try to get the x by itself. So let's add x to both sides. Okay, so let's just rewrite our equation so that we end up with x by itself. So we'll add x here, and we'll say plus x here. So we end up with 0.810 is equal to 0.748 plus x. So now how can we get x by itself? Just subtract 0.748 from both sides. And so we end up with x equal to 0.62. Okay, we can actually keep it one more sig fig there. Okay, so now, oh, I'm sorry, 0.062, not, I made a little mistake there. Okay, let me just double check that. Okay, yeah, so that's our right value. So that means that x is equal to 0.062. Okay, so now what does that give us? That gives us this equilibrium concentration. And if you'll notice, we actually already know the equilibrium concentration of our alcohol because it's the same as our acetic acid. Okay, because we're starting from the same amount, we're going down by the same amount, which means we'll have the same equilibrium concentration. Okay, so now we know everything we need to fill in our Kc expression. We just have to write out our Kc expression. So what is our Kc expression? So we'll say that Kc is equal to, remember it's products over reactants. Okay, so Kc will be equal to our only product, okay, and that's over our 2 reactants. They both just have 1s as coefficients. So just multiply them together. Okay. So now all we have to do is just plug in our numbers. So we'll say that Kc now is equal to, and we're just coming straight from our ice table. Okay, so 0.062 divided by 0.748 times 0.748. And this gives us a Kc equal to 0.11. Okay, does it ask us for anything else? Nope, it just asks us for Keq. So this is Keq or Kc. We could call it either way. I'll read the input though. Okay, that's it. Okay, now suppose we were working with pressure instead. So it says, suppose the following reaction, gaseous PCO5 is added to a 10-liter flask at an initial pressure of 0.75 atmospheres. It says when equilibrium is achieved, the pressure of chlorine was found to be 0.255 atm. It wants to know what is the equilibrium constant, Kp, for this reaction. And they give us a reaction equation. So it says PCl5 gives us PCl3 and chlorine gas. So how can I solve this? Again, it's a very similar problem in that we're given a few initial concentration, we're giving it an equilibrium concentration, and we're asked to calculate Kc. So we'll set up an ice table just like before. The main difference now is that we're talking about pressure instead of concentration. But everything else stays the same. Okay, so we know that for both of our products, we start out with nothing, so just 0. And they told us an initial concentration and an equilibrium concentration. Okay, so now we'll just fill in the ice table just like we did before. So we know these are both going down by minus x and minus x. And obviously, the reactant is going down by minus x. And our two products are going up by plus x. Okay, so let's see what we can fill in. So just based on this column, we know that if it's starting from 0, it's going up by x, then x must be equal to 0.255. Okay, that means we also know that this value is 0.255 since it's just the same, it's the exact same column, 0 plus x. Okay, and then all we have to do is subtract that same number from our initial pressure over here. Okay, so that fills in our equilibrium line completely. We can write our Kp expression. So it's the same as writing a Kc, only we're writing in terms of Kp. Okay, so the pressure of PCl3 times the pressure of chlorine gas over the pressure of PCl5. Always products over reactants. Everything has a 1 for a coefficient, so nothing squared, anything like that. So just fill in your numbers, and you end up with 0.131 for a Kp. So very much a similar process, just talking about pressure instead of concentration. So here's one for you to try. So let's suppose a tank initially contains H2S gas with a partial pressure of 10 atm at 800 Kelvin. It wants to know when the reaction 2H2S gives us 2H2 and S2 reaches equilibrium, pressure of S2 vapor is 0.020 atm, and it wants us to calculate Kp. So very similar to what we just did. Give this one a try. Let's see what you come up with. Okay, so let's take a look at this one. So let's go ahead and set up our ice table. You know what? Let's grab purple. Might be a little better for some people. Let's give it a little more contrast than that. Okay, so let's set up our ice table. Go away options. So just ICE. Oh, I didn't add enough boxes, did I? Okay, let's write ice on the outside. Let's try that. I was thinking only 3 boxes, but we can write it over here. No big deal. Okay, and then we have H2S, that's our reactant, giving us 2H2 and then S2. And it tells us initially the container contains H2 gas with a partial pressure of 10 atm. I'm going to leave off the units just for the sake of not having to write so much in the box. Okay, and it says when it reaches equilibrium, the partial pressure of S2 vapor is 0.02 atm. Okay, and it wants to know what is Kp. Okay, so remember, these are where our equilibrium arrows are. So H2S is our reactant, the other two are our products. Okay, so we know this is going down by minus x. We know this both has 0 to start from. Okay, so our initial for both of those is 0. We know they're increasing by x. Okay, and so we know that x will be equal to 0.020, just based on this column. So that means that this column is also the equilibrium concentration, or the equilibrium pressure is also 0.02. So the only thing we have left to do is to take that away from 10. I'm sorry, I made a mistake here actually. So this column is not correct. So this actually should be plus 2x. I forgot about our coefficient up there. Okay, so that makes it actually plus 2x, which means this is 0.040. Okay, so a small mistake there. Okay, which means our equilibrium for our H2S would be 10 minus 0.02, which gives us 9.98. And remember, these are all in ATM. Okay, so now it wants us to calculate Kp. So Kp will just be equal to, remember, it's products over reactants. So our products, we have H2, and that would be squared due to its coefficient, times S2 over H2S. Okay, and just plugging those numbers in, that means we have 0.040 squared times 0.02 over 9.98. And remember, these are all in atmospheres. Okay, so if we do that math real quick, we end up with Kp equal to 3.21 times 10 to the minus 7. Sorry, I forgot our coefficient again. So I made a small mistake here. That should be 2H2S, which means this should be minus 2x, which means this should actually be 10 minus 2x, which is 0.04, which just means this is 9.96, which means this number is 9.96. And that gives us an answer of 3.21 times 10 to the minus 6. So it really didn't affect our answer. Minus 7 was not correct in the first place. Okay, so that's your solution for this one. So really it's the same setup, just a little bit different in that we're dealing with pressure. Okay, let's look at another example. So it says at 700 Kelvin, 0.5 mole of HI is added to a 2-liter container and allowed to come to equilibrium. And it wants us to calculate the equilibrium concentrations, H2, I2, and HI. And they tell us the Kc value. So notice something's a little bit different about this one. They didn't give us an equilibrium concentration, but they did tell us the Kc value. So first, let's make an ice table and fill it in. So our initial concentrations are given. So they told us that we have 0.500 moles of HI, which is added to a 2-liter container, allowed to come to equilibrium. So this time they've actually told us our product rather than one of our reactants. So that's a little bit different than we're used to. Okay, what we can still do is we can calculate the initial concentration because they gave us 2 pieces of information. They told us the volume of the container and the number of moles. Okay, so those two combined give us a concentration, and we just know this time we're starting from initial of 0 H2 and initial of 0 I2. Okay, because remember, these are equilibrium reactions, so they flow in both ways. So I can start from either side, in other words. Okay, so now just fill in my x line. So this will be minus 2x. Since this time, this is our initial, and it's actually going down because we're making the other two. And it's 2x, remember, because it has this coefficient, mistake I just made. Okay, and then these will both be plus x. And they're just plus 1x because they both have 1 coefficients. So now our equilibrium lines are x, x, and 0.25 minus 2x. Okay, so we still have all x's in our equilibrium line. We actually don't know any of the equilibrium concentrations, but what we do know is the Kc. So now we can set up our equilibrium expression. So remember, Kc is equal to the products over the reactants, and this time we know the actual value is 50. So we can set this up. Okay, so we can set up that Kc is equal to 50, which is equal to Hi squared over H2 and I2. And we can just fill in our x expressions. So now we know we have 0.250 minus 2x squared over x times x. Okay, so since we have basically a squared term over a squared term, we can pop this out and just make the whole thing squared. So instead we'll have 0.250 minus 2x over x squared. So we'll square the entire term rather than squaring it individually. So what does that allow us to do? Well, now we can take the square root of both sides and get rid of our square. Okay, so we don't want that squared term. We want to get rid of it. Okay, so we'll just take the square root of both sides. So we end up with 7.1 is equal to 0.250 minus 2x over x. So now we can solve for x. So we can say 7.1x is equal to 0.250 minus 2x. So we end up with 7.1x plus 2x is equal to 0.250, and then 9.1x is equal to 0.250. Solve for x, you end up with 0.0275. Okay, so this is our x value now. Okay, so we aren't finished. So the question asked us to actually determine, so I'll go back, it asked us to actually determine the equilibrium concentrations. So now we need to take our x value and plug that into what we know. Okay, so we knew the concentration of H2 was just equal to x, and that's just from our equilibrium line. So we already know our x value, so 0.0275. I2 was also equal to x. And then the concentration of HI was equal to 0.25 minus 2x. So again, just plug in your x and do the math and solve for the concentration of HI. No big deal. So that's how we can do it if we know the Kc value. Okay, so try this one. So it says the equilibrium constant, Kc, at 425 is 55.64 for the following reaction. And here we have hydrogen plus iodine to give us 2 Hi. So it says if 1 mole of each H2 and I2 are placed in a 0.5 liter flask at 425 degrees C, what are the concentrations of H2, I2, and Hi when equilibrium is achieved? It's a very similar setup to the one we just did. Give this one a try and see what we come up with. Okay, so let's take a look at this one. So first, again, we're given a Kc value, and we can set up our Kc expression for our equations. Or for our equation, I should say. So we know it's our products over reactants. So here we have the concentration of Hi squared over concentration of H2 and the concentration of I2. And they gave us some initial concentrations. Well, they gave us the number of moles, and they told us it was in a 0.5 liter container. So we can convert that to molarity by just dividing the number of moles by the volume. Next, we can set up an ice table. Okay, so set up your ice table just as before and plug in what we know. So we know the initial concentration of Hi is 0. We know that we're growing Hi, or in other words, we're increasing Hi. So we're going to say it's plus 2x. So its equilibrium line will just be 2x. That's the easy one. Next, we know that we're starting with 2 molarity of H2 and I2. We're going down by a value of minus x, since there's only one coefficient. So their equilibrium line is 2 minus x. Now we can plug these numbers, or these values, into our Kc expression. Okay, so keeping the x terms. And we end up with 2x squared over 2 minus x times 2 minus x. So we end up with 2x squared over 2 minus x squared. And we'll do the same trick, taking the square root of both sides to get rid of our square. Sorry, these values these should be squares, not just times 2. Those should be squares. And so we can say that the square root of our x terms is equal to the square root of our Kc value. And if we take the square root, we end up with 2x over 2 minus x is equal to 7.459. And then we just have to solve for x. So first we'll multiply by 2 minus x on each side. Okay, then we can distribute that. So 7.4 times 2, 7.4 times x. So 2x is equal to that. And then we can subtract. So rearrange just to get the x term by itself. So in other words, you'll add, sorry, not subtract, add 7.459x to both sides. Okay, so this will go away, and now we end up with 2x plus 7.459x. Forget about this now. And then just solve for x by dividing by 9.459. Okay, so you get x is equal to 1.58. Okay, remember, we're looking for the concentration, so we're not quite done. Okay, so now we have to plug back into our equilibrium line. Just plug your x value in. So now H2 and I2 come out to 2 minus 1.58. Okay, and that will give you 0.42 molar for H2 and I2. And then for HI, you just say 2 times x, which is 1.58. So 2 times 1.58 is equal to 3.15 molar. Okay, and that's what the question was asking. So we're done. So just remember at the end, once you get your x value, you're not quite finished. You have to plug that back into your equilibrium line. Okay, I think that's a good place to pause this. Make sure you get a good grip on those ice tables. In the next couple of chapters, we're going to need to be able to do those very, very quickly. So make sure you get a good grip on how to solve an ice table.